if the system is expanding against a constant pressure, contracting, in other words, if work is being done on it by the surroundings plus W. And now we get to the first law of thermodynamics. But before we get to the formal definition of the first law of thermodynamics, I just want to mention something about work. We know that work equals force times displacement. We know that pressure equals force over area. So force is pressure times area, isn't it? Right, we know this from baby physics. So if I plug this equation in here, I get work equals pressure times area times displacement. And area times displacement is what? Volume. So think about this, if this is a disk, it's got a certain area, and if I displace it through a certain distance, S, what do I have? Volume, the volume of that cylinder. So area times displacement is basically base times height is volume, okay? So work, in fact, can be defined as PV in terms of thermodynamics, or P delta V. So the P here is the external pressure acting on the system, for example, atmospheric pressure, like we just saw with a piston and the potassium chlorate decomposition. And delta V is the change in volume of that system. Now there is a minus sign here, why? What does that minus sign mean? It means that work is being done on by the system. So if the thing expands against the constant pressure, it's doing work against the surroundings. So minus. Plus. Then the volume, the delta, then work is being done on the system. So it would be plus in that case. Now, this is the thing is that this is a deceptively simple equation here, P delta V, plus or minus. Let's just write that down. Plus work on system minus work done by system. In other words, translated into simple English, plus work done on system, it goes from, it gets squashed. Work done by system, it gets bigger. That's the delta V. And using the conventions we've had for plus and minus, it follows from that thing right there. Now this equation is useful if you have a constant external pressure, like atmospheric pressure. Then it's easy to calculate the work done on by the system. But unfortunately, things are not always that simple, and sometimes you have systems where the pressure is not constant and the pressure is changing. For example, here we have an example of where we have a situation where as the volume is changing, the pressure is changing as well. All right. This is quite common in thermodynamics. We have, for example, here basically various lines representing, essentially for different substances, if you will, the relationship between pressure and volume. So the take-home message is very simple. If the pressure is constant, you can use that simple equation there. If there's a change in pressure, you have to resort to integration, which is basically the same thing. You would integrate over the volume change P dV. Now basically it's nothing different than just taking that and putting an integral sign in front of it. The integral sign, all it does, this is not important for the exam, I just want to mention this. The integral sign and integration just enables us to take differential changes in the pressure into consideration. So constant pressure, change in pressure, you need to use the integral. Fact of the matter is, if a system is expanding or contracting against some external pressure, it's either doing work or work is being done on or by it. And if I heat it up or it cools down, heat is either being gained by it or being lost by it. Does everyone agree with that? And those those are the two quantities, Q and W, which define the first law of thermodynamics. This is the first law of thermodynamics in a nutshell. The internal energy, which we have a system U, this is now a new term, is the combination of kinetic and potential energy. A system only contains internal energy. So basically, this is kind of, again, a philosophical thing. U is all the energy within a thermodynamic system, locked up in the chemical bonds between the atoms moving around, you know, colliding with each other, etc., etc. We call the sum of all of that energy the internal energy U. It's all the energy. Locked up in the bonds, the thermal motion, the vibration of the atoms, everything. It's the internal energy. Now, the first law of thermodynamics, very simply, there's various versions of it. They all sort of mean the same thing. But the first law of thermodynamics is quite simply this. The change in the internal energy of a thermodynamic system equals the change in heat energy delivered to or lost by the system, and the work done on or by the system. In other words, you can determine the change in the internal energy of the system by determining how much heat energy has been lost by the system or gained by the system, and how much work has been done by the system or on the system. That's the first law of thermodynamics. Expressed differently, energy cannot be created or destroyed in the universe. That's what the first law of thermodynamics is in sort of more colloquial terms. In formal thermodynamic terms, it's this here. In fact, we should put some deltas here. The change in the internal energy equals the change in heat energy plus the change in work. I've used a capital Q, you can use a small q, it doesn't matter. Alright, so that's the first law of thermodynamics. And like I've just said, internal energy is the combination of kinetic and potential energy. The potential energy is the energy locked in the bonds of the molecules in the system, and the kinetic energy is the energy of motion, not just the energy of the molecules moving around if it's in the gas phase, but also the vibration of the atoms, right? And the system only has this energy. So if you can determine, you can't really measure the internal energy. You can measure the change in the internal energy using this expression here, which is a formulation of the first law of thermodynamics. And there it is. And that's basically all I want to say about that. You can actually do it by just pumping in heat or doing a bit of work and adding heat. This is what I really want to explain here. This is the change in the internal energy represented here, initial, final. In this case, the change in the internal energy is just equal to QV, which is being added to the system. Here it's QP plus W. In other words, in this case, what I'm trying to illustrate is I end up with the same change in the internal energy of that thermodynamic system, but I can do it in two ways. I can do it by just heating it, or I can do it by work and heat, which is essentially a reflection of this expression over here. Well, those are just arbitrary subscripts, don't worry about that.
Why would you need to know the change in the internal energy? Like, what would you?
Well, you wouldn't really use it for, well, in fact, we do use it to derive all sorts of very complex thermodynamic relations, including enthalpy. So, in fact, you need it to define enthalpy, which we will do in a moment. All right. This is another alternative formulation of the first law of thermodynamics. An isolated system is unable to exchange either heat or work to its surroundings if it's isolated. Now remember, we had three systems right at the beginning of the lecture. an open system, a closed system, and an isolated system. We said an isolated system is a system that basically does not interact at all with its surroundings, nor by energy, nor by exchange of matter. So this is another formulation of the first law of thermodynamics. An isolated system cannot lose any internal energy, right? Or that the internal energy of an isolated system is constant. The internal energy being the sum of all the potential and kinetic energy in that thermodynamic system. And here are some types of energies that contribute to the internal energy of a system: translation, rotation, vibration. These are different types of motions associated with molecules, so kinetic energy, vibrational energy, and electrostatic forces. So these are all parts, some contributions to the internal energy of a system. All right. Now, you ask, what is the importance of internal energy? The importance of internal energy is that it is directly implicated in finding or defining heat, enthalpy. And we're going to now take a break of 5 minutes.